See, PI controller, the nature of the response is, suppose if this is the set point, then this is how the response, PI controller, PI, will have oscillation. General equation for PIC is P equal to P plus PS plus Kc into E plus Kc by tau I into integral 0 to T E dt. Transfer function of PID is P by E equal to Kc into 1 plus 1 by tau I plus tau ds. So next one thing that we can do is stability. Stability. So I'll give, let's say, 6 transfer functions, 1 by s plus 1. Can we plot all the responses? 1 by s plus 1. So 1 by s minus 1. Let's say this is y1, this is y2, 1 by s, so on 1 by s, y3, 1 by s minus I. Let's say this is y4, 1 by s minus 1 minus I, 1 by s into y5 1 by s. Can you plot response of all these 6 systems? It takes some time, but just try to solve. Because from this one onwards, we will define what is the concept of stability. There is no physical significance of P, PI, and PID controller. It depends upon how do you want the response in the plant. Suppose if some offset is acceptable, then you use PI controllers. Because these are not physical things, no. These are some softwares. Controller is nothing but a software, just a simple C code. See, Y4 is S minus I. I stands for root minus 1. So let's solve one by one. So first one is simple. How do you solve? Y1 equal to 1 by s into 1 by s plus 1. So if we split into partial fractions, 1 by s minus 1 by s plus 1, 1 minus e power minus t. So y2 equal to 1 by s into 1 by s minus 1. So 1 by s minus 1 minus 1 by s. So e power t minus 1. Y3 equal to 1 by s into 1 by s, 1 by s square. So which is t. Y4 is 1 by s into 1 by s minus I. So what is the transform? How do you split 1 by s minus I minus I by s? Or let's say I. This is plus, this is minus. So basically I into 1 minus e power minus it. Y5. Y5 is 1 by s into 1 by s minus 1 minus j. J or I, both are same. So here I will not split into partial fractions. I will simply write it as a by s plus b by s minus 1 minus j. So what is the transfer function? Is a plus b into e power 1 plus I into t. Correct. Just note down, we will write it for y6 also. This is called partial fraction splitting. Somebody is asking how this has come from here to here. This is called as partial fractions. You have to write a by s plus b by s plus 1. Find out a by a and b values. No, don't solve a and b. Let's leave it as it is. I am not interested in a and b. So what is y6? 1 by s into 1 by s plus 1 minus I. So a by s plus b by s plus 1 minus I. A plus p into e power minus 1 plus I into t. Now, let's start plotting the responses. So, what is y1? What is y1 with respect to time? So, what is y1 with respect to time? 0. And then what is the final value is 1. This is y1. What is y2? Y2 will be continuously increasing. So, this is, it reaches a steady state, something like this. This is continuously increasing. This is 1 minus e power minus t. This is e power t minus 1 with respect to t. What is y3? T. Y3 is t. Can you plot y4? Can you plot what is y4? There is no rule to plot. It is functions you know. What is y4? How is it the y4 looks like? Or you just put it as, how can you write? A plus b into e power minus it. A plus b into e power minus it. What is e power it? What is a4? B plus a plus b power minus it. So how can you write e power it? Can be written as, what is e power I theta function? What is e power I theta? How can you write e power I theta? Cos theta plus I sin t. So if you see, it starts somewhere from A and then amplitude of the oscillation is B. So that is how. That is how y4 is a function of t. Just understand this function because this is how you define the stability. Take time. So everybody understood these responses. In terms of exponential, we can't define graph. What does that mean? I am not understanding. See, e power t means the graph will be exponential, no? Something like this, increasing. So this is cos t. Cos t graph will be, this is something like this. Does everybody understood these four responses? So coefficient negative and positive, let's not worry about, but just look at the trends. If it is negative, it will go on the other side. But what is important is the trends. Now out of these four, if I want to assign which one will consider it as a stable and which one will consider it as an unstable. This is a stable response. Why I am saying stable response? Because it is reaching a one final value. This is unstable response. Suppose imagine that your CSTR control you are talking. Here what happens is the temperature of the CSTR is continuously increasing. The temperature of the CSTR is continuously increasing. In the first one, CSTR temperature has increased and it has reached some final value. So this is also unstable. This is also unstable. Can you call this as stable or unstable? The fourth response. I can't call it as unstable because it is not reaching any infinity values. I can't call it as stable because it is not converging to any value. So this is called as verge of stability. We can't call this as unstable because it is not reaching any infinity values. No, it is oscillating between the two values only. Now, can you plot the Y5 and Y6 responses? Y5, Y5 and Y6 responses. What is Wi-Fi? What is Wi-Fi equation? A plus B into e power 1 plus I into t. What is Y6? A plus B into e power minus 1 plus I into t. Can you try to plot these two responses? So, is there any problem with my voice? Is there any? Can you hear my voice clearly? Can you hear my voice clearly? So how do you write this response? Now if I carefully here, if I look at this one, e power p into t plus e power it. This is a plus b into e power t cos t plus I into b power t sin t. What is the amplitude of the cos t and sin t? B into e tower. So what is the amplitude here? What is the amplitude? B into e power t. So does the amplitude increases with function of time or decreases with function of time? So it starts somewhere from A. So it will be initially amplitude is B and then it is keep on increasing. So it is amplitude is because amplitude is equal to B into e power t. So these are the real axis and imaginary axis. Or let's say we are functioning responses as a function of time. So I'm just plotting the responses. Y as a function of time. There is no imaginary axis, real axis here. These are simple responses. How? Y as a function of time. Now here, let's say just put time t equal to 0. When I put time t equal to 0, then what happens? E power 0 is 1. So it is a plus b. So this is simple a plus b. Then what is the, let's say, amplitude of the response? B into e power t. So it is keep on oscillating with response. Now here, if you see here, interesting point is a plus b into e power minus t cos t plus I into b power minus t sin t. So what is the amplitude here? B into e power minus t. So this is b into e power minus t. Now here what happens? What is the amplitude b into e power minus t? So it's come from where? But here the response is slowly decreases. So this is, so ultimately if you try to see, imaginary part has nothing to do for the response. Imaginary part is a oscillatory. So this is the response here. So you can call this as unstable. You can call this as stable. Stable, and this is unstable. Why this is becoming stable? Because of the this real part. Why this is becoming unstable? Because of this B power T. So just understand all the six responses. Take time, sit and then quietly and then understand why they are becoming stable, why they are becoming unstable. What is meant by instability is imagine that your CSTR temperature is increasing 60, 70, 80, 90, 100. That is unstable. So I'm going to leave you for some time. Just understand these responses on your own. So don't need to remember the graph. You just remember the nature of the graph. Is it increasing, decreasing, something like that? So did you get all the graphs? Now, if we go back and find out the strategy, this is stable because of e power minus t. This is unstable because of e power t. This is also unstable. You can't call this as wedge of stability. Basically, what you can say is, looking at all the transfer functions, let's say 1 by s plus 1, 1 by s minus 1, 1 by s, 1 by s minus j, 1 by s minus 1 minus j, 1 by 1 by s plus 1 minus j. So out of these 6 transfer functions, you can frame one rule. Suppose if you plot the roots of like s plus 1 is equal to 0. What is the root minus 1? So can you just locate the root? Minus 1 is here. What is the root here? S minus 1 equal to 0. What is the root? S equal to 1. So root is here. Yes, root is here. 1 by s minus j. Root is somewhere here. Here or s plus or minus j you can take. Here and here. S minus 1 minus j. Where is the root? Root is here. S plus 1 minus j. Where is the root? Root is here. So what you can say is anything which is on this side is stable. If you just find the roots of denominator, anything which is on this side is stable. So anything which is on this side is unstable. So what happens to the work? Let's say on the imaginary axis, you can call it as verge of stability. Now, important point is the origin. If you have origin, a root, let's say, here 1 by s is, we are calling it as unstable. But if you write, if you take 1 by s, if you give input, let's say only 1, then what is the response? Y equal to 1 by s, which is 1. This is stable. If you give, let's say, impulse input, unit impulse input, then the system is stable. But if you give unit step input, then this becomes 1 by s square, which is t, which is unstable. Clear? So for an input of 1 by s, it is unstable. But for an input of 1, it is stable. From 1 by s square onwards, suppose if you take, let's say this is the story of 1 by s. Suppose if I take, let's say 1 by s square. Even for 1, it is 1 by s square, which is t. Even for, let's say 1 by s, it is 1 by s cube, which is t square by 2. So what I am trying to say is, when you have roots at the origin, if you say s power m, m greater than or equal to 2, unstable. M less than 2, that means 1 is stable. So 1 by s, I am considering it as stable because if the input is 1 by s, then it is unstable. But an input of 1, it is stable. So I am taking the grace part of 1 as the input. So I am considering it as a stable function. So how do you know, let's say my control loop is stable or unstable? So basically what I'm trying to say is, so if you want to know whether my control loop is stable or unstable, take the denominator of the transfer function, equate the denominator of the transfer function to 0, find out the roots. If the roots are lying on the left side of the imaginary axis, then it is stable. If the roots are lying on the right side of the imaginary axis, then it is unstable. If the roots are lying on the imaginary axis, then they are wedge of stability. If you have more than one root at the origin, it is unstable. If you have one root at the origin, it is stable. These are the rules. Any doubts here? So, root at the origin. If you have a single root at the origin, it is stable. If you have multiple roots at the origin, it is unstable. Let's practice. Let's say 1 by s square into s plus 1 into s plus 2. Is this transfer function stable or unstable? Just keep on writing whether it is stable or unstable. So first one is stable or unstable? First one is unstable. This is unstable. Unstable. Why? Because this is the term which is making unstable. This is stable. But remember, this is unstable if the input is 1 by s. Cross mark. This is unstable if input is 1 by s. This is unstable because you have this one s minus 3. Clear? So just take 2 minutes time and read the entire analysis, whatever we have done till now. Just take 2 minutes time. Third one is unstable because of s power minus 3. Because why you have to think on this is nothing but a simple mass. Because s minus 3 on inverse Laplace transform becomes e power 3t. E power 3t, what is the value of infinity? At infinity, what is the value of e power 3t? E power infinity. So it is infinity. In the second one, we are considering input as impulse input. See, first one is unstable because of s square term, because on inverse Laplace transform it becomes t. Second one is stable because there is no unstable functions here. See, first one, even if the input is 1 by s, see, let's say I'll explain once. Take this function, let's say 1 by s square into s plus 1 into s plus 2. So this is, let's say, y by x. Y by x. So then what is a by s square? Let's take the simple input as x equal to 1. This is the simple input. Then what is a? a by s plus b by s square plus c by s plus 1 plus d by s plus 2. What happens to y of t? A, b into t, c into e power minus t, d into e power minus 2t. This is fine, this is fine, this is fine. But what happens to this one? Y of infinity is infinity. So that means it is not stable, it is continuously increasing. That is why this s square, the simplest input that you are taking is x equal to 1, which is unit impulse input. You don't need to do this analysis every time, because when you see s square on inverse Laplace transform, it becomes t. On inverse Laplace transform, it becomes t. So that means which will become infinity, and makes the function unstable. X equal to s, there is no input. No, what is x equal to s? We have defined multiple inputs. There is no x equal to s. Clear? If everybody is clear, we'll move to the next topic. To set origin, it is unstable. Why? Because see, don't let's say blindly remember the things. So two roots at the origin, but why it is unstable? Because in the mind you have to see s square on inverse Laplace transform becomes t. That is why it is unstable. So like this you have to analyze. Then only you can. Yeah, we need to consider only the real part in the complex roots, because that is what I told in all these questions. Here what we have emphasized, imaginary parts has nothing to do, because imaginary parts will become sin theta plus cos theta. The real part which is associated is becoming the functions to be make unstable. Now, suppose if I have a big transfer function, let's say y by x equal to, let's say 1 by s power 10 plus 9 s power 9 plus s power 8 plus 6 s power 7 plus s power 6, or let's say plus 10 s power 6 plus s power square plus 1. How do you define stability of this one? So to find whether y by x is stable or not, we need to find roots of s power 10 plus 9 s power 9 plus s power 8 10 power s power 6 plus s square plus 1 equal to 0. What do you call this one? This is called as characteristic equation. The denominator is equal to 0 is you call it as characteristic equation. What is the characteristic equation? Is denominator equal to 0. So this is difficult. Finding roots of this one is difficult. That is why here we need a tool to find. Do you want exactly the roots or only the nature of the roots where it is lying? Only nature. I'm not interested in actual roots also. We need a tool to find the nature of the roots. That is nothing but the Routh criterion table. So Routh criterion table is nothing but a tool which tells you the nature of the roots. So next topic is Routh criterion technique. We will take a general term a0 s power n, a1 s power n minus 1, a2 s power n minus 2, and so on, an minus 1 s plus an, which is equal to 0. This is the simple polynomial. Now we need to build a table. So how to build a table is, so this is the table. Now for the table you will get n plus 1 rows. For the table you will get n plus 1, meaning that for a third order equation you will get 4 rows. For a fourth order equation you will get 5 rows. For a 10th order equation you will get 10 plus 1 rows. So like that. Suppose if you have done mistake, then you will not get that many rows. Now let's fill the first row is, write the alternative coefficients a1 naught, a2, a4, a6 and a8. So second row is a1, a3, a5, a7, a9. So this is how you fill the first 2 rows. First 2 rows, nothing you will do, you will just fill the rows from the given equation. You will just fill the rows from the given equation. Like this and so on. So don't think that let's say I filled only A9 and all. Next rows is you have to calculate. Let's say you have to calculate B1, B2, B3, B4 and so on. How do you calculate B1? Is you take this row and from this row you will get, let's say, B1. What is the determinant of a matrix AD minus BC? I assume that this is a 2 by 2 matrix. Then what is the determinant is AD minus BC. This is simple minus of AD minus BC. That means A1, A2 minus A0 A3 divided by A1. Just imagine this one. A1 A2 minus A0 A3 divided by A1. So how do you write B2? B2 means using this one you will get B1. Similarly, this one, using this one you will get B2. So how do you write B2? A1 A4 minus A0 A5 divided by A1. Like this. Similarly, write B3. Can you write B3? So what is B3? B3 is A1 A6. Correct. Now let's write next one. What is next one is C1, C2, C3, C4 and so on. When you are writing C1, C2, C3, C4, now you have to take these two rows. These two rows and get this C1. But the concept remains same. Meaning that what is C1? You have to take these two. So that is B1 A3 minus A1 B2 divided by B1. What is C2? B1 A5 minus A1 B3 divided by B1. So like this. Can you just try one problem writing this proof? So SQ plus 5s square plus 6s plus 1 equal to 0. Can you fill the Routh criterion table for this one? Can you fill the Routh criterion table for this one? So I'm just showing the previous table. So can you fill Routh criterion table for this one? So how do you fill this? First thing is, this is a third order equation. You will get 4 rows. 1, 2, 3, 4. First 2 rows. 1 and 6, 5 and 1. What is this one? 5 into 6 minus 1 into 1 divided by 5. This value. What is this value coming? What is this value coming is 29 by 5. What is this row? 29 by, this is 0. What is this one? 29 by 5 into 1 minus 5 into 0 divided by 29 by 5. So what is this value? Is 1. That is how you fill the table. Ultimately, what you get in the table is 1, 6, 5, 1, 29 by 5, 0, 1, 1, 2, 3, 4. So now after filling the after filling this table, you have some rules to find out, let's say, whether the systems are stable or not. First thing is rule number 1. Write this rule number 1. So I'll just read, you just write in your notes. If all the elements in the first column are positive, if all the elements in the first column are positive and non-zero, positive and non-zero, then the system is stable. Then the system is stable. What does this rule is saying is, if the system is stable, then all the elements in the first column will be positive. So how do you know, let's say, whether this theorem is correct or not is, let's take a stable function. S plus 1 into S plus 2 is equal to 0. Is this stable characteristic equation or non-stable, unstable? stable. So if you expand this one, x square plus 3s plus 2 equal to 0. So if I fill the Routh criterion table here, 1 and 2 and 1 and 2 and 3. So what is the third? You will get 3 rows. 3 into 2 into 1 into 0 by 3 equal to 2. So this is positive, this is positive, this is positive. So this says Routh criterion table says it is stable, but reality is also stable. That means you are convinced about rule number 1. Now rule number 2. Write this rule number 2. If sum of the elements, sum means SOMV. If sum of the elements, if sum of the elements if sum of the elements in the first column, if sum of the elements in the first column are negative, that means it is unstable. That means it is unstable. What does that mean? Unstable means few roots are lying on right side of imaginary axis. Few roots are lying on the right side of imaginary axis. That means if some of the elements in the first column are negative, that means it is unstable. What is meant by unstable means in the Routh in that diagram, if you see, some roots are lying on the right side of the imaginary axis. Then another rule is the number of roots lying on the right side is equal to number of sign changes. The number of roots lying on the right side is equal to number of sign changes. Number of sign changes. This is the rule. Now, how do you verify rule number? Now, just read the rule number 2. We will see how to verify this rule number 2. So, what is this rule number 2 is? Suppose if I have a Routh criterion table, something like this. Or let's say, let's build a Routh criterion table, something like this. Now, let's take s plus 1 into s minus 2 into s plus 3. How many roots you have? -1, 2, -3. Basically, you are taking a known system and you are verifying. Can you build a Routh criterion table for this one? S square minus S plus -2 into S plus 3 equal to 0. S cube minus S square minus 2S plus 3S square minus 3S minus 6 equal to 0. S cube plus 2S square minus 5S minus 6 equal to 0. So can you build a Routh criterion table? 1 minus 5, 2 minus 6. What is this first element? 2 into minus 5 minus 10 plus 6 minus 4 by 2. So this is minus 2. Minus 2 into minus 6 divided by minus 2. So this will be minus 6. So this is plus. This is minus 6. Is everybody build this table? So basically this is plus, this is plus, this is minus, this is minus. So this is an indication that you have minus. This is unstable function. Now how many sign changes? Plus 2 plus sign change is 0. Plus 2 minus sign change is 1. Minus 2 minus sign change is 0. So number of sign changes is equal to 1. Number of sign changes is equal to 1. That means number of roots on the right side is equal to 1. So this is to know number of sign changes is equal to number of roots on the right side. Third row it should not be plus, it is plus 2. 2 into minus 5. 2 into minus 5 is minus 10. Minus plus 6. Is this right or wrong? Minus 2 only it is. ఏం కాకూడదు ఆరులో ఉంది. So then last one is rule number 3. Rule number 3. So write this rule number 3. So the title for this one is roots on imaginary axis. Suppose if a system has roots something like this, it has all the roots on the left side, only 2 roots on the imaginary axis. Is this system stable or unstable? This is called as verge of stability. This is called as verge of stability. The verge of stability, that means all the roots are lying on the left side, only 2 roots are lying on the imaginary axis. So write this rule. If one pair of roots in the imaginary axis, write this one. If one pair of roots on the imaginary axis, comma, equidistant from origin, comma, equidistant from origin, and all the other roots all the other roots are on the left side of the imaginary axis, are on the left side of the imaginary axis, comma, all the elements of nth row will vanish. All the elements of nth row will vanish. Equidistant from origin, and all the other roots on the left side of the imaginary axis, and all the other roots are on the left side of the imaginary axis, comma, all the elements of nth row will vanish. All the elements of nth row will vanish. And none of the elements in the preceding row, and none of the elements in the preceding row will vanish. And none of the elements in the preceding row will vanish. The location of the pair of roots, the location of the pair of roots can be found, the location of the pair of roots can be found by solving the equation CS square plus D equal to 0. CS square plus D equal to 0, where C and D, are the coefficients, of n minus 1th row, as starting from left to right. As starting from left to right. Just read this rule. See, this description, whatever told, is available in the corner. So what this rule? I'll explain the rule. Now let's take a known system, s square minus 1 into s plus 2. So what are the roots? J minus 2. Is this system verge of stability or unstable or stable? Verge of stability, no? If you do Routh, now this kind of systems you can find in the Routh criterion table as, suppose if I expand this one, SQ plus 2s square minus s minus 2 equal to 0. So now if I fill the Routh criterion table, 1 minus 1, 2 minus 2. So this is the third order equation. How many rows you will get? 1, 2, 3, 4. So what is the third order? 2 minus 2 by 0 and 0. So then there will be no term here. Nth row elements, if you get 0 and 0, it is an indication that the system is on verge of stability, which is true, no, because I have taken a system which is verge of stability. So nth row elements 0 and 0 is an indication that the system is becoming verge of stability. What is meant by verge of stability means this kind of systems where two roots on the imaginary axis and the rest of all the roots should be on the left side. Suppose if I take system like this, is this verge of stability or unstable? This is unstable. This is unstable because one root, even a single root lying on the unstable side will make the entire system to go into unstable region. For a stable system, everything should be stable. Clear? Now, what this rule says is, if you take the n minus 1th row, this will become C, this will become D. So CS square plus D will give the roots on the imaginary axis. 2s square minus 2 equal to 0. What are the roots? S equal to j minus j, which is true, no? See, what I'm trying to say in the demonstration is, I'm taking a known system and I'm verifying the theorem. So this says j and minus j are the roots, which is true because I have taken the j and minus j are the roots, no? With this one, 3 rules are over. So I think we can close here. If you have any doubts, we can continue. I will clear the doubts. Any doubts you have? Sorry, this is s square plus 1. Sorry, plus 1. S square plus 1. Then what happens? This is plus 1 plus 1. This is plus and plus. But the systems remain same. So take it as s square plus 1 into s square s plus 2. S square minus 1 means it is unstable, no? So 1, 1 and 2, 2, the entire explanation remains same, but only the equation is s cube plus 2s square plus 2. So do you have any doubts here? See, s square plus 1 I have taken now because the roots are j and minus j. That is why I have taken s square plus 1. So I think CR readouts, somebody is asking CR readout, why are reaction having high activation energy are temperature sensitive? Because you will get e power minus e by RT, no? That minus power E is high. That means even for a small changes in temperature, that power will become higher, no? Suppose let's take activation energy 0. Then what happens? E power 0 by RT. It is not temperature insensitive.